In order to establish the efficacy of a metal organic framework for any separation application, it is common practice to conduct laboratory breakthrough experiments. Such experiments are almost invariably conducted under isothermal conditions in fixed bed tubes of internal diameter 5 millimeters or so, and the length of the packed tube is approximately 100 millimeters. The morph crystals packed in the tube are usually about 5 to 10 micrometers in diameter. The inlet flow rates used in such laboratory apparatus is of the order of 2 milliliters per minute, and the interstitial gas velocity within the tube is of the order of 5 millimeters per second. Industrial PSA units operate differently, and it is common practice to operate under adiabatic conditions using pellets of about 2 to 5 millimeters in diameter in order to limit the pressure drops within the fixed bed adsorbers. The morphs would have to be incorporated to binders and pelletized for use in such industrial PSA units that have diameters perhaps in the range of 1 to 2 meters, and the height of the fixed bed adsorbers may be of the order of 5 meters. The interstitial gas velocity are significantly higher than in laboratory scale units, say of the order of half a meter per second. The analysis of breakthrough experiments and translation of such breakthrough experiments to industrial scale PSA units is an important but not trivial task. In this video presentation today, I discuss how breakthrough experiments are analyzed and how such experiments may be simulated such that the breakthrough simulations may be employed for scale up to industrial scale units. For detailed background on the breakthrough simulation methodology, I refer you to 3 of my recent papers. Watch also my presentation on simplified analysis of breakthrough experiments and transient breakthrough simulations on my YouTube channel. I illustrate the methodology for simulation of breakthrough experiments by considering the example of separation of mixtures of propyne and propadiene. Propadiene is an important feedstock for organic synthesis, and an important source of propadiene is from cracking of hydrocarbons. Propadiene is often available as a mixture with other gases such as propyne. The separation of propyne from mixtures with propadiene is difficult because of small differences in boiling points, the order of 10.8 Kelvin, and small differences in molecular sizes. This problem of separation of mixtures of propyne and propadiene is addressed in this paper published in Nature Communications in 2021, in which 4 different metal organic frameworks have been investigated and tested for separating mixtures of propyne and propadiene. A more recent development in advanced materials that is just available online describes the synthesis of a anion pillared MOF, copper, zirconium, hexafluoride, TPA, where TPA stands for tripyridine 4-yllamine. This MOF has capacious cage-like pores and specific anionic propyne trapping sites, and this development results in benchmark propyne-propadiene separation. The MOF copper zirconium F6 TPA exhibits excellent water and thermal stability. In this paper that is online in Advanced Materials, transient breakthrough experiments are reported for separation of 50-50 mixtures of propyne and propadiene at a temperature of 298 Kelvin and total pressure of 1 bar in copper zirconium hexafluoride TPA. 3 sets of breakthrough experiments are reported with 3 different inlet flow rates of the gas mixture: 0.8 milliliters per minute, 1.4 milliliters per minute, and 2 milliliters per minute. In each case, the mass of adsorbent in the bed is 0.57 grams. The dimensionless concentrations of the gas components at the exit to the fixed bed laboratory tube are plotted against the time expressed in minutes. The first step in the analysis of this set of experiments is to check the consistency of the data that is reported for 3 different flow rates. In order to test the consistency of the data, I plot the dimensionless concentration at the exit versus a modified time parameter, Q0 times T divided by mass of adsorbent, where Q0 is the flow rate of the gas mixture at the inlet, expressed in units of milliliters per minute. M sub ads is the mass of adsorbent in the bed in grams, and T is the time in minutes. This modified time parameter should, in theory, account for differences in the flow rates at the inlet and differences in the masses of adsorbent, should that be relevant. We see that the 3 sets of data collapse more or less to produce a unique curve, indicating that at first sight the data are consistent and can be analyzed further. The next step in my analysis is to see to what extent the breakthrough experiments can be predicted using the data on the unary isotherms as input parameters. So let's look at the unary isotherm data. The first step in performing breakthrough simulations for 50-50 propyne-propadiene mixtures in fixed bed tubes packed with copper zirconium F6 TPA is to analyze the unary isotherms and fit the isotherms with an appropriate model. As I've explained in other video presentations, I generally use the simplest isotherm model to start with and increase the degree of complexity only if that is absolutely necessary. For absorption of propyne and propadiene, the simplest model that is able to capture the essential isotherm characteristics is the dual site Langmuir-Freundlich model. For each guest, I use the dual site Langmuir-Freundlich model with temperature dependent parameters BA and BB as shown here. So for each guest molecule, there is a total of 8 parameters that is used, and the 8 parameters for each guest molecule is determined by fitting the 3 sets of data simultaneously for each guest. I use the Excel solver for fitting purposes. The precise procedure has been explained in previous video presentations. To demonstrate the accuracy of the dual site Langmuir-Freundlich model fits with temperature dependent parameters, I plot the component loadings against the surface potential that serves as a proxy for the spreading pressure. The surface potential at any given temperature is given by this expression, where the parameters are determined from the isotherm fits that are specified in this table. We see that the data at the T different temperatures collapse into a single curve, and that the experimental data are in good agreement with the fits that are indicated by the continuous solid line. An important advantage of using the DSLF fits with temperature dependent parameters is that this model can be differentiated to determine the isosteric heats of absorption. The isosteric heats of absorption can be determined from the Clausius-Clapeyron equation by analytic differentiation of the dual site Langmuir-Freundlich model fits with temperature dependent parameters. Now the analytic formula for the DSLF fits can be derived using Mathematica or Maple. I have used Maple, and I have programmed the calculation procedure in Excel. As I have stressed in previous video presentations on YouTube, I do not like the use of virial fits of isotherms to determine QST. The most convenient and proper procedure for determination of QST is to use isotherm fits with temperature dependent parameters. The resulting QST values determined as a function of loading are shown here for propyne and propadiene. These are the values that is reported in the advanced materials paper cited here. We now proceed to the breakthrough simulations of the set of 3 experiments for propyne propadiene mixtures at 3 different inlet gas velocities. The breakthrough simulations require the solution of the partial differential equations describing the variations of the molar concentration of each of the gas molecules C sub I at any time t and position z along the fixed bed adsorber. This is the partial differential equations that describe the component balances. The background is provided in my papers and also in my video presentation on transient breakthrough simulations. V is the interstitial gas velocity within the bed, epsilon is the bed voidage, and Q super bar is the average component loading within the crystals in the fixed bed. The average component loadings are defined as the radial average of the component loadings within the crystal at any time t, and these loadings are a function of the radial distance coordinate r. R sub c is the radius of the crystallite. The transient uptake within the crystal are described by the partial differential equation shown here, where Ni is the molar flux that is described by the Maxwell-Stefan diffusion equation. The input data on the bed voidages and the interstitial gas velocities may be determined from experiments. Epsilon is given by 1 minus m adds, where m adds is the mass of the adsorbent that is packed in the tube. This is the experimental data, and in the set of 3 experiments described earlier, this has the value of 0.57 grams. Rho is the crystal framework density. D is the inlet diameter of the tube. Length of the packed tube is L, and so this is the cross-sectional area of the tube. The superficial gas velocity is Q naught divided by the cross-sectional area of the tube, and the interstitial gas velocity is the superficial gas velocity divided by epsilon. Another parameter that is required in the simulations is the diffusional time constant, which is the Maxwell-Stefan diffusivity per each of the gas molecules divided by the square of the crystallite radius. Usually, the information on the diffusional time constant is not available, and this needs to be fitted to match the experimental breakthrough data. So we proceed in the following manner. We first perform the breakthrough experiments where the um, diffusional resistances are considered to be of negligible importance, and the component loadings within the crystallite is assumed to be in equilibrium with the gas mixture surrounding the particle or crystals. And we use the IAST for description of mixture adsorption equilibrium. That is the simplest way to perform the breakthrough simulations, and in the subsequent step we see whether a better match is obtainable with introduction of the diffusional resistances for intracrystalline diffusion. I refer you to my papers for background information. Suffice it to say that the use of the Maxwell-Stefan relations for describing intracrystalline diffusion is of vital importance for kinetic separations. Simplified approaches such as the LDF model will not work for kinetic separations, but I will discuss that in other video presentations. For the current purposes, let's proceed forward with these breakthrough model, and we first examine the simulation results for the case in which intracrystalline diffusion resistances are of negligible importance. In this paper that is online in advanced materials, transient breakthrough experiments are reported for separation of 50-50 mixtures of propyne and propadiene at a temperature of 298 Kelvin and total pressure of 1 bar in copper zirconium hexafluoride TPA. 3 sets of breakthrough experiments are reported with 3 different inlet flow rates of the gas mixture: 0.8 milliliters per minute, 1.4 milliliters per minute, and 2 milliliters per minute. In each case, the mass of adsorbent in the bed is 0.57 grams. The dimensionless concentrations of the gas components at the exit to the fixed bed laboratory tube are plotted against the time expressed in minutes. The first step in the analysis of this set of experiments is to check the consistency of the data that is reported for 3 different flow rates. In order to test the consistency of the data, I plot the dimensionless concentration at the exit versus a modified time parameter, Q0 times T divided by mass of adsorbent, where Q0 is the flow rate of the gas mixture at the inlet, expressed in units of milliliters per minute. M sub ads is the mass of adsorbent in the bed in grams, and T is the time in minutes. This modified time parameter should, in theory, account for differences in the flow rates at the inlet and differences in the masses of adsorbent, should that be relevant. We see that the 3 sets of data collapse more or less to produce a unique curve, indicating that at first sight the data are consistent and can be analyzed further. The next step in my analysis is to see to what extent the breakthrough experiments can be predicted using the data on the unary isotherms as input parameters. So let's look at the unary isotherm data. In graphs B, C, and D, I compare the experimental breakthroughs at the three different inlet gas velocities of 0.8 milliliters per minute, 1.4 milliliters per minute, and 2 milliliters per minute with breakthrough simulations, including diffusional influences. I take the diffusional time constants for each of the guests, propyne and propadiene, to be equal to one another and equal to 2 times 10⁻⁴. The match between experiments and simulations are excellent for 1.4 milliliters per minute, slightly less good for 2 milliliters per minute, and somewhat poorer for 0.8 milliliters per minute. You also note that the transient breakthrough simulations are able to pick up the distended breakthrough characteristics of the experiments very well in these two cases. But the transient breakthrough simulations are sharper for the lower inlet gas velocities. The reasons for this is because the diffusional influences are dictated by the product of the diffusional time constant and the contact time. The contact time between the gas mixture and the crystallites equals the length of the packed bed divided by the interstitial gas velocity. And the contact time decreases with increasing flow rates, and therefore the diffusional influences are stronger as the contact time decreases. I explain all of this in my paper that will be online in January 2024. Because of the influences of the contact time on the diffusional characteristics, the three simulation curves will not collapse into one single unique curve, as was the case when diffusional limitations are considered to be negligible. The important message that I want to leave behind is that a much better match with experiments are obtained for copper zirconium hexafluoride TPA if diffusional influences are taken into considerations. I will prepare more videos on diffusional influences with respect to kinetic separations in the next few days.